My talk's called PyART, Python for Remote Sensing Science. I'll get to what the acronym stands for later, but I'm actually going to acknowledge people at the beginning of my talk rather than at the end, because without these people working on the various toolkits of various ages that we've seen over this week, I wouldn't have even been able to start. So this is work I've done built on the NASA radar software libraries developed at Goddard by Bart Kelly and David Wolf, four-dimensional de-alias code by Kurt James and Bob Howes from the University of Washington, PyRSL by Eric Brunning, who is following me up, the Ball Tree class by Jake Vanderplas, NetCDF4, which is a fantastic NetCDF library by Jeff Whitaker, SciPy, NumPy, and many others. So first let's start with a warning. I'm not a developer. I am a guy who started in plasma physics, ended up getting sick of that. I became an operational meteorologist forecasting high-level turbulence and icing in Australia. Got sick of that, got sick of the shift work, so I turned into a radar guy. And working with radar data is now necessitating me to become much more of a computer guy. You can see I had a Brownian career motion. I'm very much one of these talked about users of what a lot of people do. Unfortunately, every now and then I can't find a library that does what I need to do, working with particular data sets I'm dealing with, and I develop into developer land. That's usually when either I can't find the tool or my Google foo has failed me entirely, and I find out 4 months later I wasted about a week because something already existed. Get ready to see some very ugly code. First of all, ARM. ARM stands for Atmospheric Radiation Measurement. Basically, the facility I work with is a Department of Energy user facility. We have sites across the world ranging from Oklahoma to Darwin, Australia, Manus Island, Papua New Guinea, the North Slope of Alaska. We have a mobile facility that travels the world, and basically we're there to catalogue the climate. We're there to monitor what's happening in the atmosphere to create a virtual picture of the climate in these locations to improve the representation of atmospheric processes in cloud and climate models. Traditionally, we focus very much on radiometric properties, sunlight in, sunlight out. Recently, we're starting to focus a lot more on clouds, and that's necessitated us to move into remote sensing science, particularly scanning radars. Radars that transmit beams of radiation that interacts with the atmosphere, and then we try to develop information about the atmosphere from those interactions. I'm responsible for data from two particular types of radars, a C-band radar we can see here, and an X-band radar we can see here. They operate at different wavelengths. And they're sensitive to different phenomena. That's what they look like all dressed. If we undress them, that's what's actually under the domes there. What's unique about working with these type of data sets? Well, a radar is a dish. It sends out radiation and it scans in cones. So you start with a low-level cone that gives you information at a constant angle, and you slowly image the volume of the atmosphere by doing concentric cones until you're up at the top. So we have, this is a 17 tilt scanning pattern from our C-band radar. So we deal with not necessarily exactly an unstructured data set, but a very funkily structured data set where the resolution of our instrument varies across the three-dimensional volume which it is imaging. And one of our main tasks is to take this awkward data set and make it usable to the cloud and climate modelling community. It's very hard to bridge that valley of death between observations and models, and unfortunately I'm sitting there dehydrating, drowning or whatever in the middle. So we also have a data volume issue. At each radar gate we collect about 10 measurements. There are about 983 gates along one of those rays. We do 360 samples as we go around in the cone, and we do 17 tilts. So if you want to map this 980 by 360 by 17 data set to a 200 by 200 by 17 level Cartesian grid, you do not want an order n squared process. And also these collect these radar volumes about every 10 minutes, and they run 24/7, 365, so we're continuously collecting data sets. So what's the current app ecosystem when dealing with radar data? Well, radars have been around for a while. These aren't new things. You know, they basically came around in World War I and World War II, where rainfall signals in them were actually considered a nuisance before they think, hey, we can actually do something with these. So the software is really old. It was actually developed in the age where most of the data was actually stored on tapes. So the read processes are intrinsically written in with the compute processes in a sequential manner. And it's written in Fortran, and yes, that is capital Fortran, because this is not Fortran newfangled works well. This is Fortran 77 and Fortran 90. It's not nice software to work with. And they're generally command line, parameter-based things. They're inflexible. So it was necessary for me to kind of step out and say, I'm going to do the work that nobody else wants to do. I'm not going to write another paper where I've taken 3 normal bits of code and kind of squished them together in a pipeline. I wanted to build something flexible and modular. So I talked about one of the main things we want to be able to do is map from our radius, azimuth, elevation coordinate system to a latitude, longitude, height coordinate system that a cloud and climate model generally works with. And so one of the techniques you can use for doing this is for any given XYZ position, you want to search for points from your radar data set that is within a radius of influence and do an inverse distance weighted average onto that point. And as I said, what you don't want to do is for each point in your XYZ grid, search through all the points in your radar grid in a linear fashion. One method you can use for searching your radar grid is by storing the data in a ball tree, or a C structure that's actually hierarchically structured compared to distance between the individual points. Do I know what I'm talking about here? No, I don't. That's the wonderful thing about open source software. I Googled all these things about, inverse distance, all this kind of stuff, found no Python libraries, but I found this thing called a KD tree that led me to a ball tree, that led me to a bit of code written by Jake Vanderplas that was actually used in astrophysics for doing a similar thing. I emailed Jake and said, Jake, this almost does exactly what I want. Can you add in the distance to the output as well? And Jake said, yeah, sure, and sent it off to me. And the ballsy mapper was born. So how have I implemented my gridding algorithm? Now I'm going to do the risky step of looking at code. Now, if this code doesn't work, I can just say I'm up there with the greats like Travis. But here we go. So this is my biggest discovery from this workshop is the notebook thing. I never heard about it, and I can just see so many applications for it. So here's our import here. This is where we import, that's our basic reading code there, reading in the MDV, meteorological data volumes from NCAR, and this is my mapper here, Ballsy. Go down, some bookkeeping stuff. There's where we're reading in a volume of radar data. We're doing some displacement calculations here, and then what we do for each radar gate, I tag it with its XYZ coordinates. I go down, and so this is what a typical radar, this is a typical tilt from a radar. This is the first tilt from the radar there. This is looking through a storm in Oklahoma. So this is a wonderful thing. This is I can look at what does the 10th tilt look like. Goes off and recalculates and perhaps works. There we go. So now instead of looking through the bottom of the storm, we're looking up through the anvil cloud there. But we're still not in Cartesian coordinates. I'm still looking at a tilt. So here, close to the radar, I'm down very low. Out here, I'm actually going through at about 10 kilometers. So here's where I've set up my grid, 101 points by 101 points by 31 levels, 0 to 17 kilometers. I want to look at the bottom quadrant, so Y range is minus 100 kilometers to 0 kilometers, X range is minus 50 to 50. When I call it, what I actually do, and here's the radius of influence here, which I've just done as r equals the height divided by 7 and the Euclidean distance from the radar divided by 190 plus 500 meters. These are the radius of influences which I'm going to look for points to map onto my Cartesian points, because we want it to vary because the resolution of my radar varies as I go further away as the rays diverge. Here's how we call, so there's a graph of the radius of influence there. And here's how we call the object. First of all, we column stack the X, Y, Z coordinates of my data. and we send it with the actual geophysical or the actual radar parameters at those points, and this then creates my ball tree. So the init call creates an object which is the ball tree, which I can then query with my radius of influences and my points which I want to retrieve, which is here. Ask are my positions I want to retrieve. They're my radius of influences, and this is my weighting function here. So this is what's called a Barnes weighting function. It's an inverse exponential weighting function. The further away you go, the weight of each of those points you're mapping onto your Cartesian point drops off exponentially. And this is an example of a Cressman filter. So that runs off, computes my grid. I then do a couple of bookkeeping things, and there is a Cartesian grid there. Whoops, wrong button. So this is through the 10th level there, so I'm going every 500 meters, so this is at about 5 kilometers. I can go look closer to the surface, say through level number 4, and then we can see we've got a much closer to the level thing. I can go right up to the anvil, say level 12. And we can see, yep, that I think is changing there, and there we go. Anyway, so it creates a three-dimensional grid of mapped points. And to show that it's three-dimensional, I can take it, save it as a CF-compliant netcdf file, and throw it into a three-dimensional rendering engine like Kitware's Paraview. And actually, so what we can see here, isosurfaces, or surfaces of constant reflectivity through that same thunderstorm. So we actually can see, as we pan through here, that this overshooting top here, this area of lofted up high reflectivity, is evidence of a very energetic thunderstorm and updraft. So the ARM Radar Toolkit, which is PyART, the ARM will probably be dropped once I manage to fork it out and everybody out there gets really involved in this project, and we'll call it the Advanced Radar Toolkit or something like that, Anarchist's Radar Toolkit. Follows the processes from remote sensing data to model relevant data. What do you need to do that? You need to read in the radar data object. It's not a trivial thing, because everybody who builds a new radar has a new radar data format. You need to read the data into an object, so a common object, so that if anyone wants to use it, all they need to do is build their own ingest and they're in the system. Correct the data in its native coordinates, doing things like attenuation correction, folding corrections, grid it to an XYZ grid, as I've just shown, and then because radars do not measure the atmosphere, they only measure the interaction of the radar radiation with the atmosphere, we then need to use models to retrieve geophysically relevant parameters, rainfall rate, ice water content, wind speeds, and so forth. Compute information, what cores are convective, what cores are non-convective, what's my total rainfall, what's my convective rainfall, and then write the data out to nice, neat climate forecasting convention netcdf files and share with the world. So where are we? We're very young. PyART hasn't been released yet, so instead of being Yoda or all the others there, we're just a wee little baby chomping on the meaning of life. Most of our modules exist in a prototype environment. Some are fast enough, some I've got to do a lot of work, go back into C and actually optimised. We're jumping through hoops with DOE and labs who are saying, oh no, we've got to commercialise this. Haven't you seen all the nice cars in the parking lot? Not kidding you, that's what they said to me. And I say, no, it's going to be open source because otherwise it dies. Still a lot of work to do on documentation and a lot of work just to do to write basic setup scripts. We've got a lot of C code in there, some Fortran code in there. And guess what? We're planning on hiring. So polish off your CVs if you want to come to Chicago or see me later. But of course, we're planning on hiring. The only two things in life that are certain are death and taxes. This is an FY13 position, and who knows what's going to happen between now and October. So as I said, I'm a user. So I'm here to say, pretty please, what would really help my science in terms of software development? A fast, flexible interpolation of large unstructured data onto a regular 3D grid. I'm part of the way there, but as you saw, if anyone noticed my little timings in there, it's taking me about 8 minutes per radar volume to grid at the moment. That's not fast enough if I'm going to deal with 22 radars running for the entire year 24/7. I would love to see isosurfaces in Matplotlib. You saw what I showed you from ParaView. It's a fantastic way to explore 3D data sets, and at the moment I don't like having to save data out and go to a separate app. I'd much rather be able to do that natively in Python. And an easy way to implement interactive graphics. I think this is one area IDL's got us beat. Anyone who's used IDL's widget engine, I found it quite easy to write widgets in IDL. I'm finding it not straightforward, and the ecosystem in Python is bewildering. I'm still trying to work out what the path of least resistance. Just building a really simple, I press this, my plot changes to go up through tilts, to go up through levels. So in conclusion, work is proceeding on an open source toolkit for working with scanning radar data, or it could be any scanning instrument like LiDARs and so forth. We hope to release this soon on GitHub. I've been literally today playing with GitHub and trying to get my head around how it works. It seems like the perfect place to be sharing this information. We've had great support from DOE management. This is kind of going beyond the lab level to the actual people who are funding our facility. They are very keen for open source software because they see what we do in ARM with the way we share data free and unfettered as being open source. And we're actually now starting to get it into their heads that as an agency, as a user facility, our only product doesn't need to be netcdf files and data, it can be code as well. Not only do we want to give people climate data, we want to give them the tools, the clear and easy to understand tools to unpack and work with the data. And anybody interested in the project or interested in being in the loop, that's my email. Our data, which is free, plentiful, and available as always, is available at archive.arm.gov. And to see the status of our real-time radar network, go to radar.arm.gov. And with that, I'll stop blathering.
Hey. So I've got a question about the way that you did your tree-based searching. Do you know, have you played with the point cloud library? It's a C++ library that people use for like the Xbox Connect and other kinds of LiDAR data and stuff.
No, I haven't. Is it a GPU-based thing, or?
Not explicitly. I think you probably can do GPU stuff, but no, it runs wherever.
Point cloud. I'll definitely check that out, because as I said, this is one thing you kind of get around by just Googling and latching on to the nearest things. So, you know, discovering things like Python and C types now is making me realize I should be extending my search beyond Python libraries and looking at other libraries as well. So
we've definitely had some luck using the point cloud library for doing very similar things, though instead of it's not a ball tree, it's like a, you know, n-dimensional KD tree kind of thing.
I'll check it out. Thank you.
It's really neat.
My talk's called PyART, Python for Remote Sensing Science. I'll get to what the acronym stands for later, but I'm actually going to acknowledge people at the beginning of my talk rather than at the end, because without these people working on the various toolkits of various ages that we've seen over this week, I wouldn't have even been able to start. So this is work I've done built on the NASA radar software libraries developed at Goddard by Bart Kelly and David Wolf, four-dimensional de-alias code by Kurt. Got sick of that, got sick of the shift work, so I turned into a radar guy, and working with radar data is now necessitating me to become much more of a computer guy. You can see I had a Brownian career motion. I'm very much one of these talked about users of what a lot of people do. Unfortunately, every now and then, I can't find a library that does what I need to do, working with particular data sets I'm dealing with, and I develop into developer land. That's usually when either I can't find the tool or my Google foo has failed me entirely, and I find out 4 months later I wasted about a week because something already existed. Get ready to see some very ugly code. First of all, ARM. ARM stands for Atmospheric Radiation Measurement. Basically, the facility I work with is a Department of Energy user facility. We have sites across the world, ranging from Oklahoma to Darwin, Australia, Manus Island, Papua New Guinea, the North James and Bob Howes from the University of Washington, PyRSL by Eric Brunning, who is following me up, the Ball Tree class by Jake Vanderplas, netcdf4, which is a fantastic netcdf library by Jeff Whitaker, SciPy, NumPy, and many others. So first let's start with a warning. I'm not a developer. I am a guy who started in plasma physics, ended up getting sick of that. I became an operational meteorologist forecasting high-level turbulence and icing in Australia. Slope of Alaska, we have a mobile facility that travels the world, and basically we're there to catalogue the climate. We're there to monitor what's happening in the atmosphere to create a virtual picture of the climate in these locations to improve the representation of atmospheric processes in cloud and climate models. Traditionally, we focus very much on radiometric properties, sunlight in, sunlight out. Recently, we're starting to focus a lot more on cloud.